Okay, so here's how the code works written in MATLAB. So I'll just go through each of these lines of code. So we start out, and make sure I remember to mention about the FFT. So we start with 256 points. We evenly space. There's not a huge number here. We're trying to, because it's not super rapid, this solution, because it's got a time step, and the time steps have to be quite small. So the n is 256. The x is linearly spaced between -10 and 10. And then there's our delta x, there's our delta k, and our k. So that's always going to appear in all of the problems. Okay, that's the definition of k. So then we set up here, this c equals 16u, this just sets up the initial condition. So we're going to have a solitary wave, because we want that solitary wave to just keep marching on. That's the magic of this numerical solution to the magic of the KDV. So we're going to test it with the solitary wave. This is the formula for it. And the solitary wave centered at x equals -8. And then the delta t is given by this formula here. Now you've got to be careful with the choice of delta t to make it small, and it depends on the number of points squared. So it's going to, if it increases number of points, the delta t has to get small. And there's theories around why this has to be, suitably small. So there we go. So T max is 0.1, so we're going to march forward only 0.1 of a second, and we're going to go through doing lots of little time steps, and we're going to solve only in the Fourier transform space. So the first step we do, we're just updating u. We replace u by the old value, new value replaces the old value. So we go u times, there's that function. We've got to do a dot times. That's the first step, the linear part done exactly, and then here's the inverse Fourier transform here. This funny step involving the inverse Fourier transform and all that. So we take the inverse Fourier transform to get u, we square it, find the real part, okay, just to get rid of any spurious bits that might appear because everything's real. We Fourier transform that back. So this is and there's our step size of delta t times 3ik times that. Right? So this is basically taking u, we've got an inverse Fourier, because big U is the Fourier transform, so we've got an inverse Fourier transform to get to the actual x space. We've got to square it, and then we Fourier transform that. So that's the Fourier transform of U squared, right? So to get to U, we've got an inverse Fourier transform. All right, so let's have a go at running that and see what happens. So what we want to do here, again, we've got to plot the answer. Now the answer is the x comma u, that's the initial condition, is now called u, and we've got to pronounce x comma, and we actually have to get ourselves back to the real space. So we've got to inverse Fourier transform our big U. Okay, so this is going to produce, it's going to solve this solution 0.1 of a second later. Let's try and run that code. Okay, there's the picture of it. Doesn't do a lot exciting, does it? Okay, so it's moved forward a certain amount. If I change the delta t here, so it very cleverly we'll just calculate the number of points. This is setting the step number of points to make sure that we end up getting to where we want to get to. If I run that again, the solitary wave moved on a little bit further. So nothing very exciting happens here because the solitary waves are going ding, 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 just moving along. Okay, but that is kind of amazing because it's not like a, it's a simple shift. It's a very complicated equation. It's very bizarre that it has this nonlinear equation has a solution that just sort of marches forward in time like that. Okay, so let's try and do something a bit cleverer here. So this is, we want to try and plot the output. Okay, so I've done, pulled this one out of the oven. I just fiddled the code to make sure. Maybe it would have been a good thing for me to have done this while you guys were watching, but I've got the code here working. So what we're going to do is we're going to just run this forward and do a few time steps on it. So I'm going to go forward in 20 time steps, each one by 0.02, and every time I run this code to move us forward that amount. So there's lots and lots of time steps. I'm not going to plot every time step because the computer will be here forever. Then I'm going to plot it. I'm always going to plot the initial condition, and then I'm going to pause, and we're going to loop that 20 times. So let's have a look at that, how that works here. So there it is, marching away. Not very interesting, but it's amazing, and it's perfectly capturing that soliton. Okay, so that's an achievement without a doubt. You know, the code is performing very well. There's no numerical errors. There's nothing spurious happening. All right, and we can maybe increase this to 50 so we can get a bit more excitement. Here we go. So what we want to do is something much more interesting than that. We want to do 2 solitons. And we know that the little small chappy goes faster, goes slower. So we're going to put a small one in front. So I'm going to change this initial condition. I'm going to add another soliton on. So I'm going to call that U1. And then I'm going to create another one in front, which I'm going to call U2. He's going to have half the height. The other one was height 8. So he's going to have height, he's going to only have height 8. Remember the height was half C. And I'm going to put him at -4. So I'm going to say U is U1 plus U2. Okay, now let's see what happens here. Okay, if it doesn't run, I'll quickly go, ooh. There they are. So there are the 2 solitons. So the big one is going to catch up with the small one. And if we're going to run far enough here, that's the initial condition here, the 2 solitons. He's going to pass through. I mightn't have quite done it perfectly. I don't want them to overlap here because that wouldn't be correct. So maybe need to shift him on a little bit too. Okay, it's also working pretty well. So the solitary wave, this is the crazy thing about the soliton that is really weird. The solitary wave, it passes through, there's an interaction, and then it carries on. So it's like there's no way this should happen. The things should not just be passing through each other. And not only should they not be these solutions at all, right? It's a nonlinear equation, but there shouldn't be solutions. You can see it wrapping around here. Let's just move this one here about. I'm going to shift this to 3. Oh, that does seem to work quite well. It probably doesn't matter, that little overlap here. It's close enough to 0. I just want to run this again and just show you one thing, because they pass through each other, but I'm just going to run that again. So let's just try and follow this big soliton, just sort of even moving constantly, following him. See how he's moving, speed, right? Like, he suddenly speeds up here. He's jumped ahead. He's going quicker. So he hasn't just passed through sort of smoothly, he's got catapulted forward and out. And this guy at the back has got slowed down as well. He's come backwards. Okay, so they're not, it's not as simple as when they do actually interact. They reappear, but they do feel passing through each other. There's some change. They don't just simply pass through each other. The front one gets thrown forward and the back one gets slowed down. So that's kind of crazy. All right, I'm going to show one last thing here, if I can be so bold. Okay, so what I'm going to show you now, with a little bit of fiddling, is a slightly more interesting case. So I've replaced the U by this difference of 2 hyperbolic tangents. So it's basically just a sort of a lump. There's no special structure. It's basically supposed to be some kind of region where it's, you know, just like a block, but I've tried to smooth it a little bit with the hyperbolic tangents. Okay, I've had to double the number of points here, just fiddling around with it to make it a bit more accurate for what I want to do. So let's try and run this code and see what happens. This is just to show. So that's the initial lump. Okay, so it evolves forward. So you get this trailing waves coming off the back. Probably just adjust this thing here. It does go negative, so I'm going to go down to say -3. Let's try that. So you can actually see what's going on here. Try running it again. Okay, so what happens is you get kind of trailing waves rippling off the back, and then this thing breaks into 2 solitons. There they are there, that travel forward. So whatever initial condition you give, it breaks into and can be decomposed as solitons plus this rippling part. Okay, there's the big soliton and a little soliton. If I increase the height of this thing, those solitons will change, the number will change. Okay, if I make it a little bit smaller, I'll only get 1 soliton. We have a play around with that. So this is kind of really weird behaviour. Super, super odd. What the heck's going on? Why is it producing the number? It's like it's producing this discrete number of solitons. What the hell? I'll try and see if I can show that. So I put a 3 out the front here. I should probably put these in brackets. Okay, here we go. Risk all. See what happens if I change this to be 1.5 here. I'm making them smaller. Okay, I only get 1 soliton. And he is smaller, so he goes slower. Not very exciting, is it? So I'm just shrinking that, the number of solitons. And if I try and increase this number here, what do I have before? 3. So if I go too high here, I'm going to break off the thing. I had 3, let's try 5, say. Okay, but see if we can get it to go. 12 mightn't be enough here. I'm a bit sick of that one, not very exciting, but there was only 1 soliton. Let's try this again. Okay, so it still only produces 2 solitons here. We'd have to go a bit higher to get 3. Okay. I'll make this 30. And make this, we're going to study all of this and understand this in detail. This doesn't break into 3 solitons, I give up. Here we go, there's 3 solitons. Okay, so you get a discrete number of solitons. You make the lump bigger, it breaks into different solitons with different heights. And you can calculate, there's a formula for this here. You can see a bit of crinkling here. We haven't got enough points to capture it. It's still doing pretty well, this method, isn't it? So this is crazy behavior, very weird. You can see out of these numerical simulations. And you can see that one there on the, finally here, this is the overtaking soliton in a waterfall plot. And this is supposed to show you this, you can see this one here going dong, 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 dong. And then it comes along here and suddenly it's not going at that speed. It gets flung forward. That's what this is showing you here. And the slow one gets slowed down as they overtake. Okay, I've covered all the ground there. And we'll go on to do the theory and try and understand this amazing behaviour in the next few lectures.